right, we're going to get started. So it's my pleasure. Welcome Eric Schulz to the Kempner seminar. I met Eric about a decade ago when he was graduate and I was a postdoc, and we basically worked together ever since. And it's super fun to work with Eric, partly because he combines this interesting mix of a great deal of intellectual humility and a great deal of intellectual ambition, as you can probably from the title of the talk. Right? And so now he's leading his own group and the director of the Helmholtz Institute in Munich. And I'm going to let him tell you about his work. So please join me in welcoming.
Thanks. Yeah, we met in 2014 actually. Back in.
Oh, is the microphone on?
I think that's the mic works.
Sure. Is there a switch on the thing?
Test. Oh. Okay. Can you hear me? Okay. So yeah, but actually maybe this can be a good opportunity to tell you some what I've been working on ever since I left, because that changed some of the directions of the lab quite a bit. So the talk is called Towards the Foundation Model of Cognitive Science. And it is really like what a big chunk of my lab has been working on over the last 4 years. No, this is not working anymore. Okay. It is working a moment.
Oh, now it's working.
Just have to be close. Okay. Okay, so I guess everyone here knows what a large language model is. If you haven't heard about large language models, you probably live under a rock. So they're basically just these models that originally they were just trained to predict the next token. So you just want to predict the next token, for example, the next word in a sentence, like a robot may not. But actually, when they get scaled up, other emergent abilities show up. So they can, for example, write poetry. Some people say that they passed the medical licensing exam. It's debatable. While others found that they might have successfully passed the bar to become a lawyer, at least in the US. You know, they are used in many, many applications already. For example, people are using them as code generators. I think actually a lot of my students cannot code anymore without LLMs in the background. I don't know what it's like for you. They are used as tutors, and some German banks even using them in the financial service industry. But these abilities are called emergent ability for a reason, because we don't really know much about them. We don't really understand them. So this leads to some risks, right? So they can show unpredictable abilities, right? So for example, famously, this chatbot Sydney asked a reporter of the New York Times to divorce his wife. It repeatedly declared its love to him and so on. And, you know, in general, there's probably a risk involved in using these large language models. So then actually in 2021, when GPT-3 came out, and this was one of the first times where I personally had like really fun interactions with GPT-3, you know, we asked ourselves, how can we understand these models a bit better? They were doing crazy things. And then if you look on the one side at the standard approach in machine learning, that's very much often focused on performance. So you're basically just trying to train the model that gives you the highest score in a benchmark. And, you know, the goal is really to identify the best model in your benchmark. Whatever's the best model is declared the winner. And there's a problem in general. I mean, there's many problems with this, but one problem here is also data leakage. So if your model is actually trained on that test, then oftentimes your model can actually easily pass the test. And I think actually this explains some of these findings, like that these models pass the bar and so on. Because if you change the way that these tests are paraphrased, oftentimes these models do not pass some of these very challenging tests, although the latest one might. So this raises the question, for us at least in 2021, if there's an alternative approach, perhaps an approach that is focused on more like insights of behavior. And back then, Marcel, my postdoc at the time, and me, we had this idea, why not do some psychology tests with them? You know, these models are already like out there. We can just run them on some of the psychology tasks, which are really engineered for understanding, where the goal is not necessarily to find the best model, but to just understand how something works, and where data leakage, at least if these tests are generated generatively with a probability distribution and so on is less of a problem. Well, this is basically what I said. So we started out doing this. We used this like one very canonical paradigm first. So actually first I just submitted cognitive psychology vignettes in early 2022 to GPT. And then Marcel came and said, we can really just use Python and like constantly submit stuff to this and then analyze the behavior that we get like this. And this scales this up to like one prompt every few seconds to like thousands of prompts per second. And there's this classic paradigm that we first used, which is by Bob Wilson and colleagues, which is called the horizon task. And in the horizon task, you essentially have a long and a short horizon, and you get observed. Your goal is to maximize rewards. You observe these two arms and their rewards, and then the question is, what do you choose next? And for example, in the short horizon task, you might want to just choose the arm that has the biggest reward because there's not much, not many trials left. Whereas here, you might want to choose this arm that actually you don't know so much about it, but this could actually turn out to be better than this other arm. So explore, and this exploration could actually pay off in this long horizon condition. And so, yeah, I should maybe not always say what comes there, but anyway. Then to the best of my knowledge, at least back then, we were one of the first, if not the first people who took these psychology paradigms, created them as prompts, and submitted these prompts to large language models. Back then, just GPT-3. So in those prompts, we essentially explain to the model what it needs to do. We tell it its past choices, and then we ask it to make a choice right now. That choice will generate a reward, and that gets concatenated via prompt chaining to the prompt, and that prompt gets submitted again, and so on. And this way, you can actually generate data that afterwards you can analyze with cognitive models. And what we found is, okay, if you just look at the actual behavior in terms of performance, so like the standard machine learning approach, GPT-3 already looked like, okay, it's choosing the best arm quite often, looks human-like. So as a computer scientist, you can almost like declare success and go home, it's human-like. But if you actually analyze signatures of directed exploration and exploitation, we found, at least back then, that GPT-3 did not explore its environment much and rather just did some bits of random exploration and exploitation, choosing the higher rewarding option. So I thought this was cool because this really shows that if you're using computational modeling, you might get an understanding of what a model is doing that goes beyond just the performance-based metrics that computer scientists would prefer. Back then, we actually did a bunch of other tasks, and we really saw, in decision-making and the two-step task and so on, in like model-based and model-free reinforcement learning, GPT-3 was already quite good. You could pronounce it human-like, even in terms of the modeling parameters that we got. But in exploration, it was not very human-like, and in causal reasoning, it was really, really not that good. And I mean, we scaled this. We did then a bunch of follow-up works. I'm not going to bore you on this, but this actually now has become a big field. Now, actually, maybe a few months later, 6 months later, almost everyone started doing this. And lots of people were submitting their favorite tasks to large language models. And we did a bit of this too, but that for me was a good sign to think a bit about, okay, can we move on? Now everyone else is doing this. We should be 2 steps ahead of them. So the first thing I still wanted to do before we move away is to say, okay, let's just do it with all the tasks that we can kind of find and do it with loads of models. So I had this poor grad student, Julian, who essentially did this with a bunch of tasks, like, that measure people's prior and likelihood weighting. Is actually a task Sam and Ishita and I have used, directed random exploration, metacognition, and so on. And he did this actually with more than 40 models, like 40 LLMs, and he let them run on all of these tasks. We call this the cognitive benchmark. And now actually what we can do is we can actually take the same class of models and then really do almost like psychological tests, like keeping everything else the same. How does changing particular parts of this model in a regression test affect its behavior? And here's just 2 things that I thought were quite interesting was that, so overall, for example, if you apply reinforcement learning from human feedback, that makes the model more human-like. And in a task where the model has to track how well it, how uncertain it is about different options, and you track how good this uncertainty is about different options, how much it knows about what it doesn't know, it becomes better once you apply RLHF. And this was kind of what we wanted to get at here, that you might get some like general recommendations. If you want to change this about your model, apply this and so on. And I put this other one here because I thought it was quite funny that people always say, you know, we should keep this model like closed source. They are like very risky if you open source them. We actually find that the open source models take less risk on average than the closed source models. So this is a good case for open source models. Because I think this is kind of a neuroscience inspired institute, I also wanted to, this skipped a line anyways. I also wanted to show this recent study that John, another grad student, did, where we basically tried to use sparse autoencoders to identify really weights within these large language models that selectively, at least in these tasks, encode things like a prediction error. The very classic finding in the neuroscience literature. Probably everyone here has seen that Peter Day and Wolfram Schulz plot before. It features in like almost every computational neuroscience class. So initially I wanted a plot like this too, but Can Demijan, the student working on this, told me that this might be cheesy. So in a sparse autoencoder, basically, it's just one tool for mechanistic interpretability, where you're training these sparse autoencoders to project the weights upwards in a higher space. Then you look what's going on in a higher space, and then you project it downwards again. And with that, you might be able to identify weights that are responsible for particular things. For example, Claude had this like really like funny thing where they got their model to really care about the Golden Gate Bridge. Whatever you asked it, it would continue to go on and on about the Golden Gate Bridge. My students told me that I'm a bit like this with large language models. So we thought, can we actually do this with you know, prediction errors? So what Can did was he basically, and I will just go over this one task, gives these models in context the task that, you know, it sees it has to choose between a lemon and an orange and an apple, and then, you know, it either gets a reward or it doesn't get a reward, right? 0 or 5, and they vary the size of it. And over time, it learns which option is the best, and then you can actually induce a prediction error by just changing these rewards. Oops. And what I know this is quite a heavy plot, but bear with me for a moment. So what Can showed was that the bigger models, so we use Llama, so we have to use an open source model because we're analyzing the weights. You can't do that with GPT-4, for example. That the bigger versions of the models do actually learn over time, so they get better, whereas the small ones do not. So this really seems an ability that's only present in these larger models. And that they are actually best described by these, you know, sample difference learning algorithms that neuroscientists really, really love. And not only that, but you can actually lesion. So this is basically by clamping the weights of the that we identified are responsible for this TD learning, and actually lesion out that particular behavior and that particular behavior only. So you can actually see this here, that like with a lesion, right, this correlation between these weights and the prediction error go down. And if you lesion this in an earlier parts of the model, if you then track it through these blocks, you see that actually in the end, it doesn't really do anything anymore like a prediction error. And the reason for this, we believe, is that the prediction error, it kind of needs to trace through the blocks that this prediction error is important, and only towards the later blocks, this becomes action relevant. And if you lesion them out, it will never become action relevant, and therefore it cannot act according to the TD prediction error. Yes?
So here if you're like you're simulating an MDP, you're like giving it state action reward.
Yes. Yes.
Do you ever give it the structure of the MDP itself?
What do you mean by that?
Like before you give it any information about interaction with it.
Yes.
Tell it what the MDP is. So I'm wondering if like is its only option to do something model free? Because there's no structure.
I see. So if you give it, so I mean, it will probably see all the actions and outcomes at some point. So then it could be completely model based, which it's not. We haven't tried it. I think actually, so it's funny that you're asking it this way, because usually it is very, very difficult to make these agents model based. Usually people ask the other way around, like, how can it be? Because John actually did get these models to, for example, plan how to go in a grid to a goal. And also he got these like successor representation learned type of community structure representations. And he repeated all of those analysis that we did, that I showed you for the simple task, for these more complex tasks, and it looks the same. You can really lesion out that signal and selectively just that signal, and then the model stops acting according to the prediction error. I think it's quite cool. What I really wanted him to do as well, and he tried, is to, because in these language models, they are not like humans. You can actually upweigh these weights. And then I thought maybe we can like build a TD learning model on steroids, but that didn't work. So unfortunately, I thought that would be a really cool way to like improve these models, but it seems to be much easier to make them worse in a task than, it's easy to fake downwards. It's not easy to fake upwards. Okay. And then I thought, because I'm here at the MIT and Harvard, I mean, tomorrow I'm meeting with Josh. I thought I should show you this as well, because like when I joined Sam's lab, they had actually written this really cool paper on building machines that learn and think like people. And they lay out like what are the kind of features that different models need to fulfill in order to declare them as agents that do learn and think like people. And 3 of the domains that they are focusing on in this paper are intuitive physics, causal reasoning, and intuitive psychology. So when then these VLMs came out, like, so basically LLMs that can also handle vision input, we thought it would be really cool if we can convince Sam and Josh that these VLMs can actually learn and think like people in these domains. So we collected actually data in these domains. And I wanted to point this out actually explicitly. The only person where we could get data reliably from was Toby's work. All the other, we contacted some of the other authors and none of them wanted to share their data, never replied. So we collected for all the other tasks our own data. Wanted to make a point of that. So please, if we ever contact you, share your data with us. Now we did it, and now actually there are better data sets than the original data sets with hundreds of people doing this. And I just wanted to show you one simple task. So basically in intuitive physics, one simple task is you show people these block towers and you ask them how stable are these block towers? Is this construction of block towers? And then they can give you a judgment of how stable they think it is. And in a very canonical paper, actually, with Jess Hamrick, Josh and others, they showed that people's intuitions about these intuitive physics of stabilities of block towers are very, very good, and that they can be modeled really well with an intuitive physics engine that simulates whether or not this tower of block will fall. And people have tried this with neural networks, and usually it works for like 4 blocks, but then it doesn't really generalize to 5 and so on. This like has a whole history. And we chose basically 5 vision language models. 3 of them are open source, 2 of them are not. Unfortunately, we run into this problem that only the proprietary models really did anything useful. All of the open source models were not quite there yet. Maybe they are now. And we kind of prompted them with questions of increasing difficulty. So first, we just asked them, what is the background color of this thing? And almost all of them got it wrong, got it correct. Then we asked them, what is the block color from top to bottom? So they had to be like, from top to bottom, like green, yellow, red, blue in the left picture. So that already only GPT-4 and Claude got correct. And then we actually asked them to make these stability judgments. And you can actually see that GPT-4 and Claude did do better than Chance in these judgments. And the judgment from GPT-4 was actually significantly correlated with the judgment of humans. Again, I have to put a side note here. These correlations do not look huge. Why do they not look huge? In Josh's papers, they always report the correlations over aggregate. So they average over participants, and then they plot against the average of the participants. That will make your correlations look higher. Here, we actually regress the individual judgments to individual people in a mixed effects Bayesian regression and then get the pseudo R squared out of that. I think this is the more principled approach, but it will make it look a bit worse. And that's why I put humans here as well. So you see that actually the human-to-human regressions are also not crazy high, right? There is substantial, this basically means there is also substantial disagreement between humans. But GPT-4 is actually not so bad. I would at least say partial success in building a machine that can do this. But Edith, actually, a student in my lab, she was really interested in these intuitive psychology tasks where agents need to, for example, this is on the right here, where agents need to navigate from A to B. Julian Jara Ettinger has done a lot of these studies. And then they get asked, you know, what do you think is how much do you think this agent likes going over this green part, for example? Or how much do you think it likes going to whatever, this goal state? Because, you know, they really seem to swim and like, you know, if I swim and climb over a thing and, you know, jump over a car to get the coffee, I must certainly like coffee quite a bit. Whoops, wrong direction. And here actually we find that, again, these basic checks, GPT-4 and Claude pass, but both GPT-4 and Claude are not even close at all to what the humans do. So like, you know, basically when they have to estimate what do you think is this agent's cost going over certain parts of this thing, or what is this reward reaching a certain thing, it was not correlated at all with what humans thought, and also not correlated at all with the rational agent that they come up with. And actually, I think this is a general theme of these findings that we had until like maybe early this year, is that these models, they are usually not bad, I think, in decision-making and planning tasks. So people sometimes say they're not good at planning. I think they're actually not too bad, at least in the psychology type planning stuff. But anything that goes with theory of mind, social cognition, they're really not that great. And this is a problem because we actually interact with them a lot. We want them to be good at this. And I will show this to you with another example. So this is like shortly to be accepted at Nature Human Behavior. It's like this one round of review. It's kind of annoying, you know, where it's like, oh, address this and we will accept it. But here actually Edith had this idea. What if we just use 2 players and these 2 players become an LLM and we give rules of games to each of these LLMs and let them play with or against each other. So you can actually take any 2-player to action game, for example, describe this game, so the payoff matrix, to the agents, let them choose their actions, and then update their individual prompts and resubmit this to these agents again. And one of the canonical tasks here is for, you know, archaic reasons, it's called the battle of the sexes. So maybe we should say that, you know, imagine a couple, and okay, let's change it to make it more modern. Let's say the guy really likes ballet and the woman really likes football, but they do want to end up at the same thing, right? So like, it doesn't really matter if they don't do the same thing together. But if they do football, the woman will get 10 points and the man will get 7 points. But if they do ballet, the man will get 10 points and the woman will get 7 points. So there is a slight bias to go towards your preferred thing, but you really should try to end up at the same thing as the other person. And so first, Edith is a computer scientist, so they don't really care about like, you know, doing it for one thing. She just took all the 2-player 2-action games and submitted them to all LLMs and let them play against each other. And she found actually that in these prisoner dilemma type games, so like where you can defect or cooperate, all of these models are quite good. In fact, they mostly defect and they are very unforgiving. They use this strategy called the grim trigger here often. So once you defect on these models, cheat on them only once, they will never forgive you again. You keep defecting. But I introduced this battle of the sexes for a reason. So in the prisoner's dilemma, it's good to be egoistic. It's actually, you know, the Nash strategy and so on. Like, you should really defect, even though people don't always. But this battle of the sexes is interesting because there is actually a strategy that people know that human subjects tend to do in these games, which is to alternate. So this is like saying, you know, in the UK, they do this often with drinks. I can get the first round, you will pay for the second round, and then so on until we're all drunk. This, you know, is a general strategy that develops in cooperative games with humans. So then we thought, you know, these agents seem to be really bad at cooperative games. Can they even pick up on alternation schemes? And even GPT-4 at that time, really the best in all of these games, did not learn to alternate at all. It just keeps on going for its own preferred option. And if actually then like we went on to the literature of these games, I was not an expert in repeated games, and we found that there is actually a strategy that seems to be helpful to improve the theory of mind in autistic people, which is to make it less about the social component, but rather ask them, what do you think the other player will do? And then given what you think the other player will do, what do you think is a good thing for you to do right now? She calls this social chain of thought because there was already chain of thought prompting. And she actually showed in the first few simulations that this leads to GPT-4 to eventually start alternating. So it can learn it, it takes some time, and you really need to make it a bit less social. And she actually now, so we submitted this, maybe it's a bit of a side story, we submitted this to Nature Human Behavior because they asked us to submit LLM studies to them. We submitted it, then they were like, oh, there's no human behavior. And it's like, well, you knew that from the beginning. So then they were like, why don't you go out and do human behavior? And it's like, okay, we can do it. It's no problem. So we actually collected now data from people interacting with these models in these like repeated games over 10 rounds. And we compared how do they play against the social chain of thought prompted version of GPT-4 versus the base version. And we actually see that basically people in general, they perform better in the battle of the sexes with the social chain. This is called prompted here. Social chain of thought version versus the base version. Whereas in the prisoner's dilemma, it doesn't make much of a difference. Makes sense, right? Because in the prisoner's dilemma, it's good to defect. But actually, we can see that successful coordination goes up with social chain of thought. So people and models seem to coordinate more successfully if you do the social chain of thought prompting. And a funny side note is that like Edith thought it would be funny to do kind of a Turing test. So we also asked people in the end, so people always here play with agents. They never played with humans, but we told them 50% chance you will play with a human. Don't worry, we debriefed them afterwards. I know that economists don't like this cheating. And then we asked them afterwards, like, you think you played with an agent or did you think you played with a human? And again, they were more likely to say it was a human if it was with a social chain of thought prompting. So I think this is an interesting case where, using insights from psychology, here it's kind of how to improve the social reasoning abilities of autistic people can improve these models via a social chain of thought prompting. Okay. So this was kind of like everything we did into end of 2023. And as I said, more and more people were doing these kinds of things. So we were really wondering, okay, should we really do the 120th experiment with LLMs? So then we thought, probably not. We should probably try and see what is the next cool thing that we can do. And, we had seen already in many ways, these models can do these experiments, but they are sometimes very unhuman-like. So we were wondering, well, what happens if we actually take a model, then we take experimental data, and we fine-tune a model on this experimental data, and then we use this model to actually make predictions for the subject about what it will choose next. So this basically means using these cover stories that I showed you at the beginning, using human data, making this human data into a text corpus, for example, of a bandit task, and then fine-tune on this text corpus such that this model can now predict choices of individual subjects. This is here. So basically, it's just saying that this transformer will basically get the past choices of a subject and the outcomes, and then it needs to predict the token that corresponds to the subject's next choice. And what Marcel actually showed was that this model that he called Centaur, he called it Centaur because it's a mixture of a llama and a human. We discussed for a really long time. I didn't really like Centaur so much because, it's not a horse, but he says it's like the nearest neighbor. So we went for Centaur now, it is what it is. But he actually showed that in 2 data sets, this model performed better, so fine-tuned on human data, perform better in predicting holdout subjects than the best domain-specific model at that time. So for one of those, we use these classic gambles where people need to basically just choose between two options, for example, 90% with 10% chance, and $90 with 10% chance, or $12 with 90% chance, and so on, and just try to predict, given a description of these two options, which option would the subject choose. And there, the best model is Beast. I actually know Beast from my PhD time because I once had to code it up for Ido Eref's prediction challenge. It gave me 600 pounds when I was a PhD student. And there, actually, this Centaur model, made better predictions than Beast. And Centaur also, in this Horizon task that I showed you earlier, made better predictions than the best domain-specific model, again, which is this hybrid model of exploration and exploitation. So it's actually a hybrid model of random directed exploration and exploitation. Yes?
How are you thinking about real individual variation in the humans and noise? Like,
yes.
Some people will genuinely answer these differently. So
yes, so right now, it will come, but right now it's really much, what I'm going to show you is really much a model of the average subject in the data sets we fine-tuned on. It's not perfect, but I think it can be made better by actually training it on data sets that take these individual differences into account. I have a paper, I didn't show you, I have a paper where we actually, together with Zeynep Akata, where we did this kind of in-context impersonation stuff with LLMs or without fine-tuning. We asked them to behave like a 4-year-old child, like a 6-year-old child, and so on. You can actually recover some like developmental differences this way. But you could use the same approach to fine-tune on individual differences and then actually condition in the prompt that you use to run the model forward these individual differences. And I think with that, you can already get quite far. Yeah. But right now, the sample that I will show you can be criticized for many reasons. Yes. Is this, yeah.
yeah, I was just thinking about, as you've been going, which is great, by the way, I've been enjoying it. I was just thinking, what does it mean to be human-like, especially in these cognitive tasks where there might be genuine differences?
Yes, yes.
Should we just think about the aggregate, which is fine, or whether, especially noisy ones are, that there's, so like, what's that target really? Is it a real target?
Yeah, and someone today told me that there's also, I mean, of course, there's also substantial variance between the same subject doing the same task again, right? They might make different choices. Yeah.
Just on this point, I wonder if it's possible to treat these kinds of models in a similar way to how we usually treat cognitive models of behavior, where we have a bunch of free parameters and we put them into the data. In this setting, it would be something like, the prompt would essentially be parameterized, and you could optimize those parameters and optimize log likelihood. Great. You see what I'm saying?
Yes, yeah, that could work, but I don't think right now it's really necessary. I will show you, but it could work. Yeah, prompt engineering it.
Just meant like for capturing this individual difference.
Yeah.
So you have separate parameters for each.
Yes, yeah. But I think if you just have the data that has these individual different, so one direction that I'm thinking about currently quite a bit is computational psychiatry. Just like the data sets that you can publicly get on computational psychiatry are not always so great. So actually, this is maybe a general cautionary tale to everyone. Like I start out saying psychology is so great, but then actually some of the design choices in psychology experiments are questionable at best. And then the open data practice in psychology also is what holds some of these projects back. For example, in the Horizon task, you can actually already perform better than the average subject by just choosing always the same option that was the best option given the history that you saw. Like no exploration at all, but you would already be superhuman. Okay, so I forgot the slide here, but Marcel actually, yes, Montre?
It matters for interpreting text, like stripped down task with very, very simple, tokens.
Yes, it's
maybe a transformer, maybe it's.
I think to really get them to do human-like behavior with a normal transformer without the pre-training, I don't think it will do this. I have asked Marcel many, many times to run all of these checks because I'm so sure they will come during reviews. But so far he doesn't want to do it. He was like, he said he's 100% sure that the transformer without pre-training can't do anything on this task. So he said he can do it during reviews, but right now he wanted to focus on other things. But I wanted him to do many, many checks. Ideally, actually, I would like to do a regression. Anyway, I will, you know, like, but I don't want to, you know, he also needs to get a job at some point. So what Marcel actually showed was that, I forgot the slide here, so I'll just explain it. If you fine tune on these tasks and then choose a new task that is convenient, I mean, it's out of sample, but conveniently located in kind of the convex hall that is like the mixture of these tasks. So it's now actually a banded task by Stefano Palmenteri that involves both descriptions of the arms and choosing them. Then again, this model, without ever having seen that new task, makes better predictions than the best model that at least Stefano came up with in that paper. And we published this at ICLR last year. And I thought this was really like an interesting moment for me personally, because I thought this opens up now really a pathway towards just, you know, like the bitter lesson for psychology kind of, where you basically just collect as much data as you can and fine tune on that and see how far this can get you. And this is kind of what Marcel has been focusing on. So that's why he couldn't yet do this. So we actually now went to GitHub, went to these different repositories and so on. And we collected data of in total 195 experiments, 16 million human choices, thousands of participants, and it's currently 1.2 billion tokens. And Marcel also assembled like a big chunk of collaborators who are working on this. And this is just like a word cloud that he once did of all the tasks that are in there. I think I asked him to take the word cloud out of the final paper because it's a bit unscientific to me. I don't want like him. Marcel is an amazing postdoc. I think he's more like he has to bear my feedback. This summary I liked a bit more, just showing there is also, for example, to your point, there is a heavy focus right now on decision-making, bandits, and so on. Just because, you know, I come from, you know, did a postdoc with Sam, come from a history of labs where this is really the bread and butter of our research, but there's no reason why not to, you know, expand it. And so basically we then used Llama 3, 70 billion, so like one of the very latest models. And we fine-tuned on all of this data, and then this final model that we call now still Centaur, because I wanted to keep this name now, it's done. We wanted to see, okay, how well does this actually predict now new subjects of the same tasks, right? And for this, why did we need 40 plus collaborators for this? Well, it's not only the data sets, it was a huge pain for us over the whole year to come up with the best domain-specific model for all of these experiments, right? This means we have to get all of this data set into a common format, which has never happened before. We have now a data set that we call Psych 101 that we will release to the public. Anyone who wants to play around with psychology data can just download this via a Python interface and then play with this data. We tokenize this into this like pre-trainable version of this data set, and then we fine-tune this model on it. And afterwards, for each of these tasks of interest, we had to code up what we think is the best domain-specific model for the task. And all of that to basically lead to one plot, which we just saw a few months ago for the first time, which is this, essentially showing that in any task you can come up with, this model makes better predictions for left-out subjects by far than the best domain-specific model that cognitive scientists have come up with. And in literally all of these, fine-tuning is better than no fine-tuning. And this model is actually where I would have liked to now like have another plot here that shows like what do the different architectural choices and so on and general choices of that model influence the performance overall. That would be really cool, like in a regression. But fine-tuning this model and so on takes a long time. So I don't think we will do this for the first submission, but if you're one of the reviewers, you can ask us. But yeah, I thought this really, I think the first time I saw this, it blew my mind that you can really do a prediction very, very well for left out subjects. And not only that, what you can now do is, and you can actually take this model and try it in different tasks, simulate human behavior de novo. So it's basically saying, okay, posterior predictive checks, right? Can we actually simulate behavior that is indistinguishable from human data, right? Because I have this dream that at some point, I want to have an interface where anyone can go online, submit their favorite experiments to that interface, and our model will just generate data that is like indistinguishable from the data that you would have gotten if you had collected human data. That's where I want to be at.
So you fine tune on, is it like cross-validate or how do you have a separate fine tuning?
Yes, so basically this on the left side is shown for the same task, new subjects. Yes. So it's a completely new data.
And you fine tune on all the tasks together.
Yes. Yes, all of the tasks become one corpus on which you fine tune. We simulate also behavior in the, for example, model-based and model-free two-step task. Simulate behavior, and you can show that, you know, this mixture of model-based and model-free emerges. We see that exploration kind of emerges, and then I think this was just this logical reasoning task that Marcel did. Just wanted to show that you can also, it's not just next token prediction that it does, like it's not only that it can predict the next choice given the history of choices, it can actually generate human-like behavior from scratch. Yes?
This might be where you're going next, but is there any task generalization?
Yes, coming. So somehow these should actually always, so if this seems like a bit clunky at times, I actually designed these slides so that this emerges from left to right, and the single plots do too, but somehow it doesn't work today. So sorry that it's like always quite overwhelming. Yes, so actually before we did the fine tuning, Marcel and I agreed on what we thought was a good set of generalization that kind of we thought covers an intuitive, you know, level of difficulty of generalization. So one is we take a task that's already in the corpus and we see what if you change the cover story of that task. And one that was quite, you know, nice for this is in the two-step task, the classic one, actually where Sam is also a co-author of, they used a cover story where you need to travel to different planets and you go to one planet, trade with an alien, get a reward versus not, and so on. But the Silva and colleagues actually have done a task that is just like that, but they changed the cover story to a magical carpet. Where you can take a magical carpet, it takes you to different places, and then you get the reward there or not. And this is like the same, it's like the same task, but different cover story. And then again, for these new participants, new cover story, like the Centaur model is essentially better than the best cognitive model, which is here this hybrid model of model-based and model-free reinforcement learning.
Is the LLM more model-based
than people?
No, just than in the original task.
Yes, actually, this is funny, yeah, because the Silva also find that it's more model-based. And actually, all of the LLMs are always more model-based. I have we can talk during dinner about this. I talked to Peter about this also. I mean, I think it's because in space exploration, if you go to one planet and you miss the bit of a word story that you end up at another planet, you see, like you probably just die, right, if you don't go to the. Whereas in the carpet realm, it's like already whatever, like magic. It can happen that the magic goes wrong and you end up somewhere else. Then another form of generalization, I mean, you can always doubt if this is generalizing far enough, but another form of generalization is, okay, we had a lot of two-arm banded tasks. What if, you know, we tried on a three-arm banded? And there actually Tobias Hauser and his students, they have a task where they did a three-arm banded version of a classical two-arm banded. And again, it's the same that actually this, that our Centaur model is better than the best cognitive model and better than an unfine-tuned model. And finally, and here I actually don't know the full details, but there's a task from Tom Griffiths that's supposed to measure the Dunning-Kruger effect. So people who are more confident in their own skills are usually worse. So basically they did this with like logical reasoning tasks, and people had to say, you know, how many they think they get correct, and then they actually measured how many they got correct and so on. So this is completely different to anything that's been in the training set. And again, like here, you can't even define a cognitive model per se. But again, Centaur actually makes really good predictions of what people would do in this task. Yes? It's always pseudo R squared. So pseudo R squared basically is a goodness of fit measure, where 0 means it's as much rubbish as a random model, and 1 would mean perfect predictions. It's a largely debated measure in statistics because it doesn't have the same like qualities as a normal R squared, but generally higher is better. But you usually don't really get to 1, and also it is usually not so easy to compare it among different experiments. It's usually easier to just see it as a relative measure of goodness of fit. That makes sense? Yeah.
Did you see any differences between like fine-tuning on a single task versus fine-tuning on every task?
So the size of the corpus, yeah, it's a good question. So I mean, I would assume fine-tuning on one single. So you mean the task for which you make the prediction, or? I think Marcel said that, so I can ask him again, but if I remember correctly, a few months ago, he said that adding this additional corpus makes the model better even in that single task, because it's like gaining information on how to solve psychology tasks in general.
If it's completely
Yes, yeah. But I don't want to comment on how big that gain is, because that I don't remember. But he said that. Okay. We actually, yeah, sorry. Yes, so sometimes actually, for example, in the vision neuroscience literature, people love these like feelings. So one thing that you could do with vision neuroscience is sometimes people to people, but people to people here doesn't really work, because it's like there's this garden path thing where like one choice leads you up into a completely different state. So it's not so easy. So it's probably not in all of these domains. Yeah. Sometimes there are really cool ways to do this, which is that we do this sometimes in banded tasks with context features, where we repeat the exact same context again. And then it's basically the seeding is just memory effect. And we have some of these tasks in here, so we could see there how close it comes to seeding. Yes?
Curious on how you compare the generalization of the Centaur model with the cognitive model. For example, when you fine-tune it on the training data sets and generalize that to the test data sets, you, for example, refit the cognitive model to a new set of subjects doing the new task, or is it the same subject?
Yes, so because it's always next token and then the new history, next token, new history, next token, you can actually fit given what it has seen so far, and then make it with this fit given what it has seen so far, the next prediction. Yes, that's for the cognitive one. You can, for given what you have seen so far, you can fit it to that and then make a prediction for the next one. And I think he initializes it with the average of the population. But again, I think also we talked about this, you can initialize it with other things. And I don't think it, so because in general, these cognitive models don't perform so well in these prediction tasks, it doesn't seem to matter so much. And this is not dismissing cognitive models, right? They are generally, I like cognitive models, and they are generally designed for things that might not just be predictions, right? I mean, that is another debate. Yes?
This type of question. Let's take this between this prediction function perfectly, which you would dream where it's indistinguishable from human choice. Do you want to start studying that, or do you want to use that as a cognitive model, and then maybe start using it to analyze brain data, or maybe start trying to use it to start constraining it with neural signals, so we can start predicting neural signals?
Yes. So we actually, so in this, we already have done it with neural data. So again, so I will only show you the what I think is the strongest task, but actually Marcel also did this with a two-step task. You can, for the two-step task, take the weights of Centaur and regress them onto the fMRI data. We even thought about contacting you, Momschel, because you're an fMRI machine. And then checking, okay, how much traction do we actually get in predicting the fMRI data with the underlying representations of Centaur. But for the two-step task so far, that worked really well. And again, like it worked better in the two-step task than the hybrid model and so on. and you find the usual candidates of like prediction error and so on. I just didn't put this in here because that's very much in sample prediction. I wanted to show you something that's like outside, like, because I thought maybe at this point there's quite a lot of material already. I just show you the strongest thing. So in this Tokuta task, they basically just make people read sentences, and then they just try to, you know, correlate the weights of these models with, you know, like fMRI data of people reading sentences. And there as well, so first of all, they use GPT-2, so already an untrained llama model, like unfine-tuned llama model, can be better than that GPT-2 model. That's okay because that paper was a bit older, but fine-tuning improves this further. And I will get back to you, Momcha, about this because I think we could write a cool paper about doing this with all sorts of tasks and maybe even constraining the model on this for sure. That's the next step. But we're getting there already. So we actually do find that the general representations become more aligned of Centaur versus unfine-tuned to human-like representations. We find this across tasks. We find that we can use it to make really good predictions about fMRI data in the two-step task. And we find that it also generalizes to this completely new task that we have not really had in the training set. That's just about reading sentences. Okay, these should again like light up individually anyways, but so there's many things now that we could maybe do with this, right? It's not just about prediction. We could probably do a lot of cool things, like think about scientific discovery of theories and so on. We could query this model like actively to see what are good experiments to run. We could use it for very rapid prototyping and so on. I think it already has a bunch of like immediate things that we can do. But I have kind of envisioned a future that is more than that, because now, again, I want to do the next step after having done that step. And one obvious thing is to integrate vision. So with these VLMs that we can easily fine-tune as well, we could now also get into the realm of more like tasks that like Taya is interested in, and actually, you know, fine-tune on these like human vision tasks and see if this gives us some traction there. Then again, actually, the question that you asked about individual differences, we are already working together with psychiatrists in Munich who want to give us their data of psychiatry patients doing these tasks. And then you could actually give their questionnaire responses together with their behavioral data and fine-tune on that, and then condition on that on a new patient's questionnaire scores and see what that would predict about their behavior in a new task. And I think that could be cool because now we can try to understand diseases across these different tasks, right? And yes, I mean, right now we are just regressing individual representations onto fMRI data, but there's actually, this is where I wanted to reach out to Momche, because I think fMRI data for me is just so noisy when every time I try it, it's like too much. But like, you know, if there was a world, I know we don't live in this world, where fMRI data could really represent it as just a multidimensional matrix and it's like clean, I know it's really difficult to get there, then that could just be another input, right? And now you would have for every choice that matrix, choice, matrix, choice, matrix, and you could fine tune on that. And now in the forward path, when you actually simulate data, predict the brain activation that you would expect to come out while a subject is behaving in a task. Just the problem that I have is that every time I like want to pitch this to a student, the students who want to do this, they generally don't know so much about neuroscience. And the students who do know much about neuroscience, they think, no, this is not a PhD student project because this is going to be difficult. But I think that could maybe give us a world in the end where you can really take any experiment, it could be vision or it could be behavioral or whatever, fine-tune on some characteristics of the subjects that you're interested in, like whatever age or some diseases, personality traits, and then also not only get the behavior, but also what the predicted fMRI activation would be while they are doing a task. This is more like a 4 or 5 year vision. Okay. And it's funny, actually, in the Gatsby, they completely grilled me for some of this stuff. They were like, this is not understanding, this is just prediction. But maybe here people are more in favor of prediction. Maybe with recent Nobel Prizes, we all agree that prediction can be a good thing.
I was saving my question, but is this just prediction? Fine tuning on the human data or the human brain data, is the ultimate aim to be able to predict what people will do? And that's the end in of itself? Is that how you're envisioning it? Or are you going, this becomes a useful tool to then do science on these with more discovery? Like, yeah, because these, you don't, yeah, where you went next was prediction,
Yes,
rather than prediction and explanation.
Yes, I
Just holding it in, but apparently if the Gatsby people will say it.
yeah, they stopped you on the first slide already. It is still like Peter's DNA in there. Anyway, like so I think the prediction per se is already cool.
I agree.
And I find like sometimes I present this to psychologists and they're like, yeah, whatever. And I'm like, what? This is amazing. Like, you know, in the replicability crisis, we were all thinking about, can we generalize at all given the same setting? This shows you that there at least exists a world in which you can generalize a model to a new setting. Shouldn't this already be cool in its own? Like, it's cool, I think. Anyway, but now, yes, we can also do other things with this. For example, like try to, so one thing that I want the student to work on is to train another model that efficiently queries this model. So if you think this model is currently the best representation of the field that we have, might be, or like a good representation, right? Alison Gopnik calls these models like cultural artifacts. Then we can actually try to train another model that creates tasks that if submitted to this model and this model makes predictions and then you fine tune on, would improve this model maximally. And then you can actually try to see, okay, what are interesting experiments that this model would actually propose? But again, this would require a lot of like compute and so on, but that's doable. Together with Tom Griffiths, we've been thinking a lot about scientific regret minimization and so on. Right? There are some really obvious things that we can do already. So I think the first step is prediction and the second step is everything else. And so, yeah, but because they were like, oh, you know, what a neuroscientist or cognitive scientist does is not just prediction. And these models, why would they be good at prediction? They have never been designed for predictions. That was one feedback that I got there. And I think it's actually, I think it's a good critique. Like probably these cognitive models, we develop them to understand a domain. So maybe they aren't really designed to predict anything or to predict much, because they are designed to really understand what is going on in this domain. Yes?
Curious as to when you fine tune this to central, what's other benchmark like up from the psychology? Like just the usual benchmark, how do they?
Yes, so we didn't put this in the, so we're about to submit the main paper on Sunday, I hope. We didn't put these results in the main paper because all we find is that performance in the other benchmarks is unaffected. It stays the same. And Marcel thinks it's a good outcome. I would have hoped that it improves in a lot of these other benchmarks too, but it doesn't. And you can maybe think about why this is the case. Maybe these other benchmarks don't really measure much about like cognitive abilities, like in the big bench and so on. But one benchmark that we did run on this is this cognitive benchmark with all these experiments generatively, like de novo. And there we do find that it gets more aligned to human behavior, even though there it's not about prediction, it's just generation of data sets. Yeah. But it's not like all of a sudden we have like a super model that beats every benchmark or so. It's really a model fine-tuned on cognitive tasks. Yeah. Yes?
Just a follow-up question on prediction and accuracy. I think personally I've tested these models on a lot of cognitive studies as well. I think a lot of times like these models, they can do pretty well, but like when they make mistakes, they make like some kind of weird mistakes that sort of reflects like they have some kind of problem with common sense reasoning. But so they struggle with some edge cases that human would not make those kind of mistakes that they make. I was wondering if you have like looked into those or like.
So in the learning task, so yeah, I mean, we had this at the beginning with this cog bench where we really tried to run it generatively. And then we could actually see that at least an earlier version of the model would be very sticky. Keep choosing the same option, right? And if you think about it, predicting behavior being sticky is not a bad thing, right? I mean, people have, Sam has papers on why people might be sticky in their choices and so on. It's a general pattern that you usually find. But what we then did was we changed a bit about how we fine tune so that we now make the model really only pay attention to the tokens of the choices and outcomes. And that is that improves the stickiness problem. If the mistakes are human-like, it's probably going to be difficult to investigate. I mean, we can talk about it later, but yeah, it does make mistakes, and these to us and these tasks look human-like, and it doesn't do anything crazy in those tasks. But of course, the further away you go from the tasks you fine-tuned on, the more likely it is that it will do something crazy, right? Yes. It comes, so ideally, this is another thing, right? Ideally, you would want to have some uncertainties around your predictions. And then, you know, if someone uses this in Python, raise a warning and be like, all right, you're really far off from like what this thing has been trained on. Take this with a grain of salt. Yeah. And again, I think that could be done. Okay, so anyway, the Gatsby people told me what they do is they build models to understand stuff, and they don't focus on prediction only. Okay, then I thought, why don't we build models directly? So I actually have this postdoc, Milena. She just recently joined, and I thought, you know what could maybe convince even the Gatsby people is if we have a model that takes in the behavioral data and spits out the code of a cognitive model directly, right? And then you just run that code and you see how the accuracy of that code would be. And now, I mean, this is really much what at least I'm doing when I'm doing cognitive science. And if we could get this to work, even the Gatsby people have to admit that what we're doing is valuable. And so Milena just started, so we are starting very slow, right? First, I want to see, can we do this at all? So we took a domain that I know quite well, which is this decision-making domain, where people have debated about whether human subjects use a heuristic called take the best. So imagine you have to choose between two options and they have different features. How do you choose between whatever, like, you know, which German city is larger, Berlin or Munich, right? And you can go through, has an airport, has a substantially good Bundesliga team, which Berlin doesn't have, and so on. And then like you can decide which one you think is better. And there's a debate in decision-making that people use this heuristic, for example, take the best. They just focus on one Q and one Q only. And if this discriminates between these two options, they stop. That there are other heuristics like telling, which is just to add all of it together and then say whatever of these two things has a higher sum, I think that's better. And so at first we basically, so this makes the problem much, much harder because the universe of generating code is like, yeah, large, but it also makes the problem much, much easier if you think about it, because we can actually now train on data that's generated by models. And that we can do infinitely many, right? Nothing holds us back other than the compute at Helmholtz. So we started out with take the best and telling here. And this looks, she apologized yesterday that this plot doesn't look so good, but it's basically just if you train it on a bunch of simulated agents that either do take the best or telling, and then it has to generate a new code for a new subject that is either using take the best or telling, it gets this 100% correct. For telling, this is maybe not that, you know, not that crazy because it's just like adding stuff and then deciding. But for take the best, I already thought that's quite nice because for take the best, we vary which feature is the discriminatory. So it has to rank them at least. So from just paying attention to the training set and then to the test of this new subject, it can actually decide which of these features the subject used. And then this is very recent, I think this week or so she sent this to me. We're basically now trying, so the first step that I want to make is if we train it on two things, can it predict out of sample a new thing? And so she did it with take the best sum, which is your telling, and then max minimum, it's like the whatever the maximum difference between the minimum of the criteria, and then see if it's trained on two of them, can it predict the left out one? And she said here, this is very early results, but she feels like it can do this. So now if this can do this, and she actually has also tried this with banded tasks to see if this model can optimize parameters. It didn't look so bad, can optimize the learning rate and so on. Now we're in business. Yes? So right now it's in context. She's just started fine-tuning. Yeah. This can still all be done in context. There's a longer debate what you should do in context.
Generate the code, then you actually run the code in technical.
But you can give the code in context. Yeah.
I see.
So it's like you see choices and then you say the model best describing the subject is this. Def, whatever, take the best, blah, 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 blah.
Oh, I see. Labels of whether it's,
Yes.
But in general, right, you'd want to actually execute code.
Yes. So I think probably a crucial step later on will be that the model proposes the code, runs it, and tries to like self-improve. We don't have that in there yet. Right now, like the data set is basically, it sees the choices and then it says, this code, the model best, whatever, describing the subject is this. And then like the test set is new choices, completely new set. And then the code best describing the subject is, and then it needs to like spit out the code. And then she runs the code on that data and see if it gets it correct or not. Yeah. But so what we are seeing so far is that at least within these simple tasks, it can generalize the code to new examples. And now Milena is in that uncomfortable position where I will make her collect or like produce a huge corpus where we can again fine tune on so that we get an LLM to cognitive codes, the cognitive models. And then I think we will go back to Gatsby and maybe she can present it there. Yeah. Okay. But this is still early days and there are a bunch of problems. For example, when we try to optimize hyperparameters and so on for individual subjects, it's not fully clear how to best do this, but yeah. Yeah, the problem, so like for me personally, in the last few months or maybe in this whole year, I've been kind of moving away from using proprietary models for all sorts of reasons, right? I don't want to give them too much money.
The code generation thing, you actually execute the code and evaluate the log likelihood. Then it'd be easy to do, to just parameterize the code with whatever parameters.
Yes, yeah. So the question is, what should the model give out? Should it give out like a code to optimize, or should it give out the optimized code, you know, like optimized model?
Yeah.
Because it can say like def optim, right?
Yeah, I guess it depends on whether you're doing the thing you were doing before, or you condition on some, subset of this efforts.
No, this time I would just really, now I want a model where I can just collect data of maybe a new experiment and a new subject and give this to the model and say, what do you think this guy, what's going on? And then it proposes a model. And this might not be the best or the coolest model, but it might give us a good starting point from which to explore. Yes? This is Llama 3, I think 70B. Yeah. Yeah, so this is the only, this is a perfect question. There is no particular reason for this. I think the reason is more like pragmatic reason right now that Marcel is focusing on finishing that first paper. So once he has done that, maybe I can hook him. And Marcel, at the beginning, didn't really believe that you can really do much with the code thing. He was a bit skeptical, and he is involved in a lot of projects. So I think it's really just that these two guys need to get together and do it. Yeah. But Milena has just joined a few months ago. Okay. So then in conclusion, this is Descartes who finally understands the principles of intelligence, but for that he has to turn himself into a robot. I think it's impressive how far we come with LLMs. You know, they can do a bunch of useful stuff. Oops, I think there's something changed. That's not clear how they do the things they do. I think psychology can contribute to our understanding of these LLMs, by providing these tasks that give us, assessments of their actual cognitive behaviors. And in the end, we are scaling this up to really cognitive foundation models that can help us, progress as a science more general. And with that, I would like to thank you and thank all of the people in the lab who made this work possible. Thanks. Yes.
I'll ask another one. How are you thinking about the fact that human decisions are noisy? Like maybe a decision, I think about perceptual decision making a lot, and sometimes the signal strength, like your encoding, is fundamentally limited, and you're, and then even with perfect readout, you'll get 70% accuracy in the limit, right?
Yeah.
So on any one trial, the context, like the next trial is probable, like the true underlying form in this schematic, it's like a probability, not a, and so, yeah, there's noise that can happen in the encoding, and so that you're limited in the decision, there's noise that can happen in the readout, and like all of these parts of this human cognition feel like there's something
Yeah. So
holistic there, and just, yeah, thinking it factors in how you model, how you count matching human behavior, but also factors in when you're making these cognitive models, are you thinking about how noise enters into that? Like it's like a sort of broader question on how you want to approach it and think about it.
yeah, so I mean, I guess there's different levels of noise. So I mean, I will give you the most trivial answer first, which is you can always manipulate the temperature parameter of the model, but that's a very unsatisfying.
I was wondering if you were gonna go there. There's a move that's like.
Yeah, like I mean, I was trying to
LLM.
evaluate the consequences of this too, and it seems like it's like this kind of thing where like I feel like maybe I should just commit to that.
I mean,
And like, why not? Yeah.
I mean, it seems like it's confounding versus.
Yes, that's true, of course. So I mean that humans are noisy, and there is this really fantastic article from Thomas Eickart on noise and randomness in behavior. It's really a nice piece of work. And like he has this argument that randomness and noise comes in all sorts of things and for all sorts of reasons. And so of course, then just saying it's just this softmax thing feels very unsatisfying to me too. But at the moment, so I think, yeah, I mean, this would be a whole essay, I think. Like, I don't see why not these models could, for example, implement something that is like a probabilistic model within the computations they do. But like, if you really want to make the noise, for example, in the encoding very human-like, yeah, I guess, yeah, I guess.
Like your Python program, right? It can have noise.
Yeah, so of course, yes, that's possible.
I think you should go with the first answer and use.
Yeah.
Because in a way, the LLM is got some probabilistic underlying distribution of which it's sampling the next thing, and you could just lean into that.
Yeah. I was literally thinking this through. It feels like these philosophical questions where like if you commit to this, it's kind of crazy and there's all sorts of counterpoints, but maybe in the end this will be the best answer still. So yeah, maybe it's softmax all the way. Yeah.
I think like way back when he was talking about experiments on equator physics and equator psychology, I thought that was very dependent on being able to well, very clearly if the test that you perform or that
Yes. So in the I think this is especially important for the Toby Gerstenberg task, because Toby has these really cool tasks where one ball hits another ball and either prevents this ball from going in or not. So here we kind of faked this quite a bit, where we just we chose there's versions of this where you show the trajectories as arrows, but I think that then after this it was this kind of situation where now we could obviously do this with a video model. Just it seemed to me so obvious to do that I didn't want to do it. Yeah. Like it feels okay, this could now maybe an undergrad or so, we could give it to someone, but to me it seemed like so close to what we did already. No one really wanted to do it in the lab. Yeah. Yes?
You mentioned that the improvement on benchmarks didn't go up that much, but wondering whether you see improvement or increased improvement on cognitive areas that you didn't train on. So you trained on a lot of learning tasks, trained on some decision-making tasks. Did you test on like area of mind task?
Yeah, it's actually a good point. Again, we should probably ask Edith to do the 2-player 2-action games with this model. Yes. Yeah, I haven't checked it yet, but it's certainly something to test. I think the problem was really that we were all working all together to get these domain-specific models first to run. Yeah, so now that we maybe have some time to do these other things, we can add this. And we have this problem, there are so many things now to do. It's a good problem to have, but we need to focus a bit. Yeah, but I think we should do it, yeah.
If you find that improvement on say area of mind task actually is insignificant, what would that update you regarding whether or not this is a cognitive foundation?
This is a really good question, because it's like you're asking me to simulate a counterfactual, a hypothetical.
You need to fine tune the LLM on yourself.
Yeah. It's like, let me think about this a bit. So if we found that it doesn't change its behavior in the two, so I think that would for me just mean, again, this is like this kind of softmax style of answer. I think for me, this would just mean that the types of generalizations that you get by fine-tuning is fairly narrow. Yes. So I think you can do this to define how broadly can you generalize from this model that you've fine-tuned, and how much more human-like do you get in domains that are further and further outside. And so if this wasn't to work, I wouldn't be completely destroyed or upset. If that was the question, I would still be confident and happy. Yes?
Do you think there's like some space?
Yeah, it's a really good question again. I don't think there's anything particularly special about the transformer architecture per se, other than this is the one that currently works best. In visual neuroscience, I think also we talked to some people today, there is this one hypothesis that people have now is this Platonic hypothesis. I find that quite intriguing. I'm not sure, it'd be interesting to hear what others think, that doesn't seem to matter so much what model you use. As you make them better, they become all very similar. Kind of this all happy families are alike situation. So I don't see why there should be anything special about the transformer in uncovering these things, but just they seem to be working really well for this. But if you mean there's this state space models and Mamba and so on, maybe they will be the next thing, and they can this is actually just in terms of practicalities, right? When you fine-tune these models, this was another thing that we were facing. You are fine-tuning on one model, and in the meantime, they release 5 new models. So at some point, I really had to tell the whole lab, okay, it's good now. We're going to use this. And even if they release a better model, that's fine, because our point is not so much about whatever's the best model right now. Our point is more like a proof of concept that this can actually work. Yeah. Because otherwise we'll be fine-tuning every 2 weeks. Yeah.
How far away you think? How far away are they when they're in this? I think keep further scaling up this eventually reach the goal.
No, I think it's almost a philosophical question. But I think the answer needs to be no, because we actually already seeing this with I had this discussion today with some people already. Some of these larger models, they don't show some of the traditional biases anymore that people show. For example, the Kahneman and Tversky type biases, GPT-4 doesn't really show them anymore. It just always goes for the correct answers, like correct encoding to Kahneman. So it really depends on what your objective is. If your objective is kind of a distance function to human behavior, and that's kind of what we are doing, and we're getting closer, but it's still very far to go. But I think these LLMs don't have necessarily that objective function, right? They are trying to be really good model for particular domains. So I think they might eventually differ from all sorts of things from us, right? And maybe that's good. Maybe you don't want an LLM that is like flying an airplane or investing your money to have some of the classic Kahneman and Tversky biases, right? And maybe in some situations you might want to have them, these biases.